Dr. Kunkee received his PhD in electrical engineering from Georgia Tech in 1995, and he joined the Aerospace Corporation, and is currently a principal engineer and scientist with Sensor Systems Subdivision. He has so many contributions to the field of geoscience and remote sensing. I have to read a lot of them, but
this from the computer. We wanted to try to get the online.
Satellite System Division as part of the Defense Weather Satellite System and Weather System Follow-on Program Office. More recently, Dr. Kunkee was the past president of the IEEE Geoscience Remote Sensing Society and Technical Program Committee co-chair for IGARS 2023. He was co-chair of the 2017 IGARS and served as co-chair of the Technical Program Committee for IGARS 2010. Dr. Kunkee is a vice chair of USNC URSI Commission F and has served on the U.S. National Academy's Committee on Radio Frequencies, including its Committee on Scientific Use of Radio Spectrum. With that, Dr. Kunkee, the floor is yours. Thank you so much.
Well, thank you, Sam, for the kind introduction. I was looking to see where I could go to full screen here, but it seems to be kind of covered up. Maybe down here in this one. F5. Okay. All right, thanks. So I'm going to give a little bit of background in microwave remote sensing and some of the scanning configurations of the sensors. We're going to talk about microwave remote sensing sensors. Again, in the context of space-based environmental monitoring. Orbits, microwave imaging, atmospheric temperature and moisture profiling, and then little systems overview, and calibration and validation of the sensors. So this is what makes the sensors really different than a lot of other electronics that get flown in space, for communication systems. Communication systems or radio systems that are designed not for remote sensing are designed with margin for radio links. You put them up, you turn them on, and there's not a lot of calibration associated with that. In contrast to Earth remote sensing instruments, where you really are looking at characterizing the detailed characteristics of the antenna pattern as it is shown on the Earth. All of that is very necessary to be able to intercalibrate sensors, and that's important because sensor lifetimes on orbit are 5 years, maybe 10 years maximum, or unless you're doing some high quality geosynchronous orbits. But generally LEO sensors last between 5 and 10 years. So if you're trying to do climate studies, a really important aspect of climate studies is being able to intercalibrate sensors. So you have to launch one before the other one breaks to be able to intercalibrate them so that you can determine these multi-decadal trends. It's really important. You can't do that unless you do detailed calibration and validation. So even in this series of operational sensors, for the case of that I'm going to talk about, special sensor microwave imager sounder, some of you may have known about it, others not. But it is a microwave instrument that does imaging on the Earth, and it was very important for determining the snow cover and ice cover at the poles. It was the first time that we were able to unabatedly monitor really the ice on a global scale on both poles. Each sensor that we've put up is different in calibration and validation, so it's very important to do these intercal and cal-val efforts. It's really they take several months typically when you launch a sensor. So I'll talk a little bit about that. Those are some of the more interesting contributions that we do, and then to talk about the environmental products that we can get from some of these. So why do we use microwave sensors? So VIIRS, visible infrared radiometry suite. It senses in the long wave, viz shortwave, long wave, but even at the long waves, all you see from space is the outline of the storm. So you have a hurricane, you can judge by how big it is, how strong it is. A lot of times the Dvorak method is something that's used. Basically, you draw a circle around this, and the radius of that circle from these clouds represents roughly 50-kilometer winds or something, and that's that's the technique that was used for years. But with microwave, you can start to see the insides of the storm, whether it's using radar, such as a dual precipitation rainfall radar on GPM, which some of you may be familiar with, 13 and 35 gigahertz K and KA band. Or you can also start to look at the interior, the cloud, the cloud life cycle, the rain bands they call them. You can see that with microwave sensors at 37 gigahertz and 89 gigahertz, and gives you a lot more information about the storm. So this complements electro-optic sensors and really critical to understand where the storm is. And that's one of the main uses of microwave imagery. So passive microwave in particular. So microwave comes in two flavors: active for, you have radar. There's forms of cloud radar. You probably heard of CloudSat, which operates at 94 gigahertz. It's for characterizing clouds. Dual precipitation radar, K 13 and 35, 5 gigahertz for characterizing rain. And then there's also synthetic aperture radar, which is is used for a variety of other techniques, such as interferometry, such as NISAR at L and S band. So those are different types of radar for different types of observing different types of variables, Earth variables. But I'm going to talk a little bit about passive microwave. So this is it listens to microwave emission. Thermal emission from the Earth. And this is black body, probably heard of black body emission. So everything that's warm emits microwave and radiation over the electromagnetic spectrum. And in the case of the warm Earth, we can monitor that from space and look at how the Earth looks at different brightness temperatures over the ocean and over the land, and tell something about the characterization of the atmosphere. The upwelling radiation from the surface of the Earth can be completely characterized by 4 variables: vertically polarized intensity, a horizontally polarized intensity, the correlation of the instantaneous variations between those two, and the quadrature variations between those two, because it's a Gaussian process. So four parameters: a mean and a standard deviation, essentially, in 2 polarizations of the expanding sphere. So on the surface of the sphere, you have two polarizations that are characterized by these 4 parameters. So by measuring those 4 polarizations from space, we can get all the information that the Earth is willing to give us, essentially, from passive microwave emission. That's different than active. Radar, you send a signal, you look at the reflection, whether it's the backward scattered reflection or the forward scattered reflection. So this is passive that I'm going to focus on in this case. So when we look at the Earth from space, you can see that in the atmosphere, there's certain molecules in the atmosphere absorb, and certain portions of the atmosphere are transparent. So in the case of looking over the ocean, we see that the ocean is a more reflective surface. So if our sensor is looking down at the Earth over the ocean, we see the reflection of cold space from the ocean. Whereas over land, if the channel is transparent, we see the warm emission of the land, because land is basically a pretty good emitter at these frequencies. So along the x-axis, we have frequency in gigahertz, from 1 gigahertz to 150, I guess, what we do there. And these, the y-axis is the brightness temperature. So it's in the microwave part of the spectrum, the intensity of the radiation is linearly proportional to the temperature of the black body. So this is why we talk in terms of brightness temperature instead of radiance. So here, though, at 60 gigahertz, what's going on to change that? So the atmosphere is actually blocking the emission from the Earth. Again, we're looking down at the Earth over land, and we see that absorption in the atmosphere. So we're actually looking at the temperature at different levels within the atmosphere as a function of frequency within this little band. That's a really important phenomenon that we use to gather temperature profiles within the atmosphere. using passive microwave radiometers from space. It's so important. It's the most important input to numeric weather forecast models for determining atmospheric state. Another important phenomena is not shown here. It's on 183 gigahertz. But I also wanted to emphasize 118 gigahertz is also an oxygen absorption band. So when you monitor those frequencies, you can actually tell something about the temperature profile in the atmosphere. And that's a really important aspect for remote sensing. How do the sensors work? So there's two general configurations for the sensors. There's conical scanning and there's cross-track scanning. Cross-track scanning, the sensor looks and scans back and forth as the track moves along the surface, the ground track moves along the earth. And a conical configuration spins and looks at an oblique angle. Well, if it spins and looks at an oblique angle, it is such that the antenna polarization is maintained as the instrument scans. So you can differentiate. So the ocean, is a polarizing surface. You've seen the Polaroid sunglass ads. It does the same thing at microwaves. So you can tell something about the ocean will polarize the reflections from the surface emission that comes off of it and the reflected emission from the background. And so understanding the magnitude of or brightness temperature in one polarization versus another polarization gives you that additional information. Remember the 4 parameters that I showed with the black body radiation? You really need this scanning configuration to be able to monitor those polarizations at every incidence. So you really create a raster scan essentially by just scanning this footprint across the earth. Okay, and then for the cases of a sounder, here using a conical configuration for a sound gauge. If you look at those particular frequencies within the atmosphere that are absorbing, you can think of it. I'll just regress a little bit to emphasize this concept. If you think about a radio transmitter from space and a ground receiver, you really need to have a transparent window in the atmosphere, one that doesn't absorb the signal to be able to talk to the ground. It's the same with passive emissions. So think about the Earth emission rising up through the atmosphere. If the atmosphere is not transparent, it's going to be absorbed by the atmosphere. And what you're actually going to see is emission from the atmosphere itself, not from the ground, because the atmosphere absorption is blocking the view of the ground, just like a cloud. So in these frequencies, which we're looking at to get the atmospheric temperature profile, you can think of, depending upon what frequency you're using, the amount of total absorption, you can kind of pick your frequency and pick your level that you're monitoring within the atmosphere. And so this is a little cartoon that shows the emission from the atmosphere that the sensor sees at different levels. Okay, so let me give a graphic of how the sensor scans, and I think it will actually run. So you have two polar orbiting configurations, and these are sun synchronous orbits. Notice that the orbits don't move with respect to the sun. The instrument, the conical center spins. The feed horn is on the spinning portion. And it's measuring radiation from the antenna that's upwelling as the beam. So really, we're operating as a receiver that's scanning, and it draws out a path or a swath every time it goes around the Earth. So each orbit is about 90 minutes. It's sun synchronous. So with respect to the sun, these orbit planes stay fixed. So as the Earth rotates, the orbit plane stays with respect to the sun in the same orientation. So it goes over any place on Earth at the same solar time every day. That's another important concept for doing things like soil moisture, where you want to measure the emission from the ground, which changes as a function of the wetness of the ground. You want to measure that at the same time during the day to be able to get a record of how And so you use orbits like this to be able to accomplish that. So I'll just let you look at this one more time. Multiple orbit planes means that the refresh time, the place where the satellite goes overhead is every 3 hours. The instrument rotates. You've got upwelling radiation that bounces off of the reflector into the feed horn. Along the lines, this is a secondary beam that shows the upwelling radiation coming in. The calibration loads on the sensor are the other aspect there that's not shown. But this is the swath that then is carried out. So you get over a period of 24 hours, you get the full coverage, or actually 12 hours because you've got the front side and the back side. So every 12 hours per orbit plane, you get a coverage generally of the Earth. So I don't know if that concept is new, or some of you may be familiar with that or not, but that's an important aspect of operational systems that have to monitor every place on Earth regularly. So if you look at the orbit planes from the northern hemisphere, the low Earth orbit sun synchronous systems will usually pick a certain plane. So we have 1730 local time ascending node. So that means as it's going over the equator north, then at 5:30 p.m. every day, you've got this orbit plane which stays fixed with respect to the sun, which is at this point. So midnight is this midnight on the Earth is straight ahead, and the sun is at this point. So the overall aspect of multiple populating multiple sun synchronous orbit planes means that you get a repetition of observations over places on the Earth. So over the combination of ESA, NASA, the China and Japan assets, each place on Earth is imaged something like 80 times a day. That's a lot of data. And so that's, and it's organizations like this that combine, there's different assets here. I guess these are the US assets, polar orbiting environmental systems. So this is like the 2000s, early 2000s, but this is how we collect atmospheric temperature profiles and surface information on a regular basis to feed numerical and climate models. Okay, so and I'll skip this one for now. And this just shows, in the conical scan configuration, the instrument will scan a line, and then it'll do a calibration exercise, scan another line, and it just you get spatial coverage then imaging this whole entire swath. Okay, how am I doing on time? All right. So a little bit more on temperature and moisture sounding. This is enabled by the high absorption from oxygen and water molecules. Here again is the transmittance of the atmosphere. So we'll do temperature sounding at 50 gigahertz. The moisture absorption is typically at 183.31. The second most important measurement is the absorption due to moisture in the atmosphere. If you think about it, oxygen is a good molecule to sense for temperature because oxygen is uniformly distributed over the world. So no matter where you measure this, you'll get the same absorption as a function of altitude. Whereas with water and moisture in the atmosphere, moisture is anything but evenly distributed over the Earth. So you use the temperature profile and information that you get from water absorption then to determine where things like clouds are, what the moisture profile is. So the combination of those is a very powerful combination for numerical weather prediction. And again, another graphic that shows how the atmosphere affects the microwave transmission through it. There's oxygen, which is stable over, oxygen absorption is the same over the entire world, whereas water vapor will move around. This whole absorption line moves up and down. It'll move up and down depending upon the water content in the atmosphere. So what we're looking at here, the x-axis is frequency from megahertz up to through 300 and some gigahertz, and this is a log scale absorption. So really at the center of these lines, with 100 dB of absorption, you're only going to be seeing the top of the atmosphere. So that's how you sense the temperature, the top of the atmosphere, by looking at these brightness temperature measurements at specific frequencies that are really high absorption. Okay, and this is just to show that there's sensitivity curves. As you change in frequency, you're sensitive to the emission of or various things on land, whether it's vegetation cover, which also emits and absorbs, or whether it's integrated water vapor in the atmosphere. So these are just general curves that show how you use a combination of frequencies to remote sense various environmental parameters. So remote sensing is the art of looking at how the atmosphere and Earth affect what you're measuring and try to unwind all the effects that are determining what brightness temperature you measure at as a function of frequency. That's what remote sensing is all about. So for instance, when you want to measure ocean surface temperature. And so you might use a frequency that, changes, the reflection of the ocean changes as a function of temperature. But the real problem is that the reflection from the ocean changes with a bunch of other parameters too, with wind roughened ocean. There's also signals due to salinity. And so each channel has a different sensitivity. Each frequency may be a little bit more or a little bit less sensitive to each of those parameters. So by measuring several of those frequencies, then you can kind of unwind with a lot of in situ measurements or other instruments that are sensitive to yet other parameters. You can unwind really the parameter that you're looking for. In this case, it might be integrated. If you're looking for, let's say, an atmospheric variable, then you really want to include maybe a 25 or a 20 gigahertz channel because there's a short absorption line there. But you might have clouds that are also impacting the amount of water vapor. So if you want to determine where the clouds are and remove those, then you look at some other frequencies that may be sensitive to clouds and less sensitive to clouds. So you use a combination of frequencies then to optimize your algorithms. And this is, before you even consider the latest techniques of AI or machine learning. I mean, this chart goes back to just the sensitivity curves when we were using statistics. Okay, and then the same over ocean. You've got just a different structure of the ocean because the ocean is more reflective. So what do the instruments actually measure? So this is an example of 6.9 gigahertz brightness temperature over land. So you can see, first of all, the sharp contrast between ocean and land. The ocean being much colder, because what's happening there is you're seeing sort of a reflection of cold space. Land is warm, emissive, and then you're seeing probably not a lot of contribution from the atmosphere because the atmosphere is very transparent at 6 gigahertz. So you don't see a lot of clouds. You see variation in land emissivity. And so you use some gigahertz for soil moisture measurements, for instance, where you don't want to be sensitive to clouds. You want to be sensitive to vegetation and surface water content. 10 gigahertz is similar. These images were actually shown to be a radio frequency interference. We were concerned about radio sources interfering with surface measurements, and that's where we can see these perturbations. But I'm just trying to explain also the physics of what the instruments measure. Okay, and then here's another example of the difference between 19 gigahertz and 92 gigahertz. So 92 gigahertz has it's a window frequency, so it's not really on an absorption line of any of the molecules that exist in the atmosphere, but it's really more sensitive to the water vapor continuum, and it has just generally more absorption due to moisture, but it's not super sensitive to moisture. It's one of those kind of in-between channels, whereas 19 is more transparent. So this is an image of Hurricane Katrina as it's, just south of Louisiana there. And so you see much different things in these two channels. 19 gigahertz, you can see the warming of the storm. The storm is internal structure is warm with respect to the background of the ocean. And so you can see, some of the structure within the storm there that is deep within the storm. At 92, you're much more sensitive to water in the atmosphere, and in particular high altitude ice. So ice, frozen water is much more the dielectric constant of ice is very different than water. It's much more reflective. And depending upon the size of the ice particles, it can be very reflective. So what's happening at 92 is the high altitude ice of the storm is actually showing a reflection of the cold background. So the tops of the storm, you can tell have ice ambles on the top of them. But you're not really seeing into the storm so much as you will with 19 gigahertz. And all of these other blue spots here are other convective storms over the continent. Yeah, question. Sorry? The light. Oh, okay. So you remember the image with the swaths that I showed the simulation, the movie. So this is the gaps between the sensor swath between one orbit is not overlapping with that of the other orbit. So there's a gap in between. So this is just 3 revs of the instrument. And there's a gap between each of the revs. So ideally, we would design the sensor to have a wider swath, so there would not be a gap there. But because of the sensor scanning configuration and the fact that we can't really look at too high of an angle, we have to kind of limit the swath. Does that make sense? Okay, and and so for temperature, so just an example of some temperature sounding. So the structure of the atmosphere, it decreases until you get to the tropopause, where the water basically stops. The temperature changes. So understanding the nuances of the temperature profile and where the sensor measures that profile is very challenging. So each one of these is a weighting function. It tells you where the instrument or that particular channel of the instrument tells you the altitude that instrument is going to be, or that channel is sensitive to. So depending upon, if you're right in the middle of the absorption line, you get higher absorption. You're going to be sensitive to the higher part of the mesosphere, even 75 kilometers. Microwave allows you to sense among the highest levels in the atmosphere this way, from what's called off-nadir sounding. That's what we're talking about. Limb sounding is different, where you actually point horizontally and look through a larger optical length. This is called off-nadir. So you look from nadir out to about 50 degrees to create the swath. And so you can see the sampling then of the temperature profile, weighting functions. So what's actually going on is that there's a lot of finely split absorption lines within the O2 molecule. At higher altitudes, those lines are narrowed, but in lower altitudes where you have a lot of atmospheric pressure, Doppler broadening broadens out that complex set of lines. And so you have, as a function of frequency, you have increasing attenuation in the atmosphere as you get towards the center. That increase in attenuation allows you to kind of pick a frequency and pick your height of the atmosphere. And that's the whole aspect behind atmospheric temperature sounding. So another example, using the special sensor microwave imager sounder, I picked out 3 channels that really show the difference. This curve increases, decreases, increases, so on and so forth. This is the one near the surface, and you can see that this is, again, the one with Katrina. So this is, I believe, early August 2005. So you can see that the southern hemisphere is colder than the northern hemisphere at the lower level. That reverses at the tropopause, you get a different structure. And then again, at the mesopause, you get a different structure altogether. So it's just showing that you can sample different levels of the atmosphere through this set of 24 channels that SSMIS has. And then I mentioned also that the red line, which is oxygen absorption, is stable. Oxygen, we hope, doesn't change or vary too much over the surface of the Earth. You can breathe just as easily anywhere on the surface. But water vapor is very different. So this whole line changes. And so the brightness temperature changes as a function of how dense the water is. And so the channels also, depending upon which channel you sense, whether it's in the center where it's most sensitive, or whether it's in the periphery where it's less sensitive, you can see that at 23 gigahertz, you can still see the land-ocean boundary. So you're sensitive to the surface. Whereas with the more opaque channels within the moisture, you kind of see, in some cases, the boundary goes away. So where you have a lot of moisture, it's continuous across the boundary. Where you don't have moisture, you see the sharp land-ocean boundary. So that just tells you that you sense basically where the clouds and moisture are in the Earth. And you can see from the configuration, those look like moisture or cloud structure. Okay, just a little bit about data processing. I mentioned CalVal, and it's, just want to check time here. I want to leave a little bit of time for questions. During the CalVal, we look at the operational data processing. Typically, we'll have the satellite will downlink and all of the algorithms then that calibrate the instrument. So basically, downlink bits. You turn the bits into with microwave instruments, you turn them into temperatures using the calibration observations of the sensor on orbit. You then correct for all the other idiosyncrasies of the antenna pattern or other blockages of the sensor. And that's what takes time once you launch the sensor. So you get a sensor data product, sensor data record, and that's a calibrated radiance. That's a level one, what we call level one data. And then you use an algorithm, whether that be simple regression that we used in the 80s or 90s to any type of physical iterative retrieval schemes that we have now to get an environmental data record. And that processing is done typically on the ground and products that are output and distributed to the community in the operational realm. And I guess that's really what I wanted to talk about. I have some additional charts. There's a lot of products, environmental data records that are produced by optical and microwave instruments. And I have a little bit of discussion on CalVal. This is just a structure showing all of the errors that we systematically look at with the sensors when we launch them. From field of view intrusions, polarization rotation, making sure that polarization of the instrument is aligned with the Earth over the entire scan. We do simulations of the brightness temperatures, then we measure what the instrument looks like to make sure there's no systematic errors. And then we intercalibrate that with other instruments to make sure there's no biases with the set of data that we're going to be looking at for this 5 years versus the previous 5 years. Just an example, one of the first things we always do when we launch a new sensor is to ensure that we have accurate geolocation, and that's typically done by land-ocean boundaries that have a lot of contrast. Just an example of some of the microwave instruments and atmospheric sounders, which are generally smaller because they use a little bit higher frequencies. And just an example of EDR. So I'll do this real quickly. The soil moisture is one of the things that I mentioned, which is based upon the emissions from the ground. Whether the ground is saturated, it changes the dielectric constant, which would change the reflections from space and the surface emission. We can measure that using these sensors. We can measure wind direction by looking at the emission from the ocean. If you look obliquely at upwind versus downwind, the brightness temperature will be different. We can sense that and determine the wind direction. You can also look at the intensity of hurricanes One of the things that we do is look at the sea surface temperature in the track of the hurricane. That's one of the key aspects of rapid intensification of hurricanes, is how much energy it can suck basically out of the water. So if it traces back over cold water, it's not going to gain typically the intensity as if it tracks over warm water. And then all sorts of water type of, microwaves is the way to keep track of water in the atmosphere. It has, in terms of quantity, electro-optic sensors, such as visible and infrared. They can, measure once they become very saturated very quickly with any type of water cloud content in the atmosphere. Microwave can quantify that amount of water very well, so that's one of the strengths. And then rain rate. You've probably heard of the Global Precipitation Measuring Mission that was just dedicated to giving rapid updates of rain over the globe. And I mentioned earlier the sea ice record. Here you can determine the difference between new ice and multi-year ice. When ice forms, initially the salt will leach out of the water and it'll change the dielectric constant. So we can tell whether the ice has been there for 1 year or whether it was newly formed. And then temperature profiles. And it's very interesting of temperature profiles in the mesosphere. And some long-term assessments. And let's see. I think that's about it. I don't want to keep you too long. I know that we were a little late getting started, and some of you may have questions. So I guess I'll just wrap that up there, and thank you very much for listening.
So the floor is open. Have any question? We have a few minutes. So is there any difference or consideration for passive measurement, whether that is day or night?
No, because it's thermal emission. It doesn't depend upon solar reflection. So in the VIIRS instrument that I mentioned, the visible and near IR, that depends upon the solar reflection from the surface. VIIRS also has long wave bands, which are thermal emission, and that's true for microwave as well. Day, night, it doesn't matter. Yeah. Yeah.
How reliable are the retrievals in very complex environments?
In very complex. Yeah, that's so in the mountains, if you're looking at soil moisture in the mountains, yeah, that's one of the biggest challenges of microwave. It's very sensitive to soil moisture, but the footprints are very large, 40 kilometers or so. So there's a lot of heterogeneity over land. And so if it does really well if you're on a prairie, and it's the same for a long ways. But yeah, when you really get to a lot of topography, then you've got to take that into account. And it's typically done by multiple sensors that have higher resolution in some sort of data fusion, to look at, to really characterize what the larger footprint is seeing. It's a challenging problem. Yeah.
Yeah. Thank you so much. Is this similar to how Landsat and Otis with these temperature products are made, or are those kind of?
Yeah, very, very much. So Landsat is a very high resolution. I don't know the wavelengths, but I think it's thermal emission as well. The key is it's very high resolution. So you can apply some of those same techniques at long wave, in cloud-free conditions. So you're a lot more sensitive to the atmosphere. That's one of the key things, is removing the effects of the atmosphere. But Landsat is specifically designed with a narrow, it has a narrower swath, but much higher resolution to take into account the heterogeneity over land, to do some of these same things. Land cover is a big thing with Landsat, and the health of species. They can tell how stressed crops are by emissions in certain wavelengths. Yeah.
So I'll just check it on something. So is this slide deck going to be shared?
Yeah, it's publicly released, so I think I could share it. I want to check first though, but check that. Most of it's old, these old images I was talking about, Katrina from 2005. So, but the physics should all be the same. So I hope to put more viz near IR in here, but Micro is really my first specialty, so thank you for listening to this niche. All right, I hope to see you all at IGARS. I know some of you won't be able to make it, but it was certainly a pleasure coming out here and meeting all of you. So thank you.